Welcome to the world of Sanjoy's Geometrifying Trigonometry. In the previous videos, we have already talked several kind of things regarding GT simplex plus GT simplex makes a lot set. GT simplex multiplied with GT simplex make a GT simplex, but that is also a lot set. We have discussed that lot set plus lot set forms a lot set minus lot set also a lot set. GT simplex divided by GT simplex is a triangle, which is also a GT simplex or a lot set. Lot set is a bigger thing, GT simplex is a part of lot set. We have already discussed. And ultimately, every interaction in geometrifying trigonometry are done through the output line segments, and every GT simplex have a common given line segment and output line segments are different. Similarly, for every lot set, the initial given line segment is same. Ultimately, for any given trigonometry expression, we develop the left hand side, right hand side, and any kind of part of the trigonometry expressions are started from single common given line segment. If that common line segment is moved on the 2D plane, the whole GT simplexes and all lot sets which are attached to that initial line segment will also move together. If we scale the initial line segment, then whole thing will also scaled up. If we rotate the initial line segment, then the whole bunch of the line segments which are entangled with each other and forming the GT simplexes and lot sets will also rotate or transform with the initial line segment. So we cannot move any single line segment in the GT simplexes or lot set in a given trigonometry expression until all of the whole sets are moved, and all of the whole set of the line segments are aligned in a certain geometric way as per the construction protocols well defined as per the axioms of geometrifying trigonometry. There are a large set of axioms in geometrifying trigonometry because geometrifying trigonometry is not only a theoretical subject, it is a practical subject, and CAD programming, ProEngineer programming, AutoCAD programming are all done on this basis. The axioms are designed while the programming were done and the API system was developed. Whatever the assumptions we had to consider for angle calculations or for parsing the trigonometry expressions are all incorporated into the axioms of geometrifying trigonometry, such that we can avoid any kind of ambiguity in real constructions. We had to avoid any kind of ambiguity, we had to avoid any kind of fallacies or any kind of paradoxes that could happen are all taken care, because the programming is done and implemented in C# and Python and also in Java, and some C++ modules are also under preparation. The trigonometry expressions are parsed, and for different values of seed angles, it can have different large number of line segments entangled with each other, and they all move. In our previous videos, we have already shown that how all these line segments togetherly move as an entangled, geometrically entangled entities, all are geometrically related in that way. So we cannot say that 1 plus cos theta plus sin theta is same as cos theta plus sin theta plus 1. These things are not same. We will explain these kind of things there. In this special video, we are trying to explain some more thing also, that is, in geometrifying trigonometry, one concept is there, THEP, that is THEP arrangement system, that is for the respect of Thales, Hipparchus, Euclid, Pythagoras, and after that Ptolemy also. We have not taken Ptolemy there because Ptolemy had made those Almagest and those trigonometry chart and tables were made. Before Ptolemy, the whole trigonometry was done geometrically, and after Ptolemy, for the next 1400 years, the trigonometry is converted into almost algebra. But geometrifying trigonometry is trying to explain modern trigonometry in terms of the way Pythagoras, Euclid used to do trigonometry. We are trying to examine trigonometry with machine learnings, with artificial intelligence, but we have the fundamental motive that we will treat trigonometry as Hipparchus used to treat it. We will treat trigonometry as Pythagoras used to do the trigonometry. entirely geometrically, we will examine trigonometry as Euclid used to formulate the formulas at that time, at 300 BCE, before Ptolemy, and Hipparchus also made it in the 120 BCE, when the algebraic formulation of trigonometry was not there. Everything was treated geometrically, and line segment was the most important thing while dealing the trigonometry in the starting days. We have modern tools now. We have machine learning systems, we have automated geometry generation systems, we have AutoCAD, we have ProEngineer, we have CATIA, we have ANSYS, we have geometry expression, we have GeoGebra, we have several intelligent geometry calculations, we have Python, we have Java, we have C#, but we are trying to examine all numbers as triangles and all triangles as numbers, as we used to do at the time of Archimedes, Pythagoras, or Hipparchus, or Euclid. So in Sanjana's Geometrifying Trigonometry, the fundamental motive is to do trigonometry as a special kind of trigonometry where it is treated not algebraically, it is treated entirely with line segments. Circles are also secondary. Circles are not so much important in geometrifying trigonometry. In geometrifying trigonometry, points, lines, line segments, and triangles are the main players. Triangles are glued, like these kind of images. The triangles are glued and they form GT simplexes, and you can see that for every kind of trigonometry expressions, some line segments are taken as 1. In geometrifying trigonometry, that is treated as L, because that gives us more intuitive understanding, and all other line segments are somehow directly or indirectly related to that initial line segment. Some of the line segments are exactly same length of the initial line segment. They are treated as 1 in these kind of pictures, and these kind of pictures are GT simplexes, and when multiples of GT simplexes are added or subtracted, then they form the locked sets. Until the addition or subtraction are done, they are not locked set actually, and only glued form of these pictures of glued form of triangles, multiple triangles glued in some common edges, these kind of things form the GT simplexes. And here we will examine first, before entering into the THEP arrangements, we will try to examine these things with some few fundamental formulas, because these kind of understandings will help every students or every people to grasp into the factors of line segments, to think everything as a line segment. And we have kept the pictures here also. In Wikipedia also you will get these kind of pictures, in several books also you will get these kind of pictures. But we have a practice to convert the pictures into trigonometry expressions, but there was no practice before Sanjana's Geometrifying Trigonometry, and there was no algorithm, there was no canonically formalized framework before Sanjana's Geometrifying Trigonometry, which was trying to do the reverse journey. The reverse journey here is, given any trigonometry expression, we will convert that methodically with computers directly to the pictures, and not only one picture. There are multiple thousands of varieties of such pictures can happen. It depends upon the complexity of the trigonometry expression, and all of these pictures are valid, equally valid, but some of the construction will take minimum energy, and minimum energy configurations are taken as the best configuration, because ultimately when designing bridges, or for designing the protein folding algorithms, or for DNA structure analysis, or for RNA structure analysis, or for cancer cell mutation analysis, geometric analysis of the protein positioning, repositioning things, and this kind of plate folding cases where energy handling is very necessary to calculate the entropies, the hidden energies, these kind of things are necessary. So the one configuration takes more energy to get the transformation of line segments, and some other configuration takes less energy to get the geometric configuration. So we will take the configuration which takes minimum energy to get that configuration. We will discuss in our later videos with more detail for every expressions of exercise books in our school days problems are treated with the high-end models, and we will get much number of more topological questions also. We can do several geometric questions, we can do several topological inquiries on every trigonometry expressions, and this kind of endeavor was not done before Samyana's geometrifying trigonometry. So this is becoming a very interesting subject, because every trigonometry expression becomes a geometry. It has some topological data mining facilities, and now we can inquire several topological questions to the trigonometry expressions. This kind of data mining over the line segments, large number of line segments so formed due to the algorithmic parsing of trigonometry expression was not there before Samyana's geometrifying trigonometry. Now, how to examine this kind of trigonometry expression? Suppose it is said that sine square theta is equal to 1 minus cos 2 theta by 2. Here, how we will examine this? In the left hand side, we will take it as the sine square theta by 1, that is the sine square theta by L. That means L into sine square theta by L, that is on the left hand side, which means L is a given line segment, and from that given line segment, L into sine theta is prepared like this kind of pictures here below, and that is the 2 times sine theta is glued. That is sine theta, there is a theta and there is a 2 theta, so two different kind of similar triangles are interacting here. On the left hand side only one theta is there, and on the right hand side we have found one expression where 2 theta is there. So two different kind of triangles are interacting here. On the left hand side we have seen a sine square theta, which means sine theta into sine theta. So from the initial given line segment L, we are getting L sine theta. For that we are getting the perpendicular of one line segment, perpendicular of a triangle where L is the hypotenuse, and now that perpendicular turns into the hypotenuse of the second triangle, and align and scale to fit is done. So a second triangle is drawn taking as the L into sine theta, that is the perpendicular of the first triangle, as the hypotenuse of the second triangle. In that way, one hypotenuse is glued with one perpendicular. In that way, two triangles are glued here on the left hand side, and that is giving us another perpendicular, that is L into sine theta, that is a perpendicular line segment which is forming due to the double perpendicular. One time perpendicular is taken from hypotenuse, and again that perpendicular is taken as the hypotenuse of the second triangle, and align and scale to fit is done. So there are 16 type of pictures will form on the left hand side. In the similar way, on the right hand side, in the bottom we have seen the 2 is there, which means 2 times L, that is the L is a given line segment whose double length is taken, and that line segment is transformed into another line segment which is L minus L cos 2 theta, where another triangle is drawn whose seed angle is 2 theta, and now that is having a base, and that base is subtracted from L, and L is a GT simplex, and L into cos 2 theta is another GT simplex. When we subtract one GT simplex with another GT simplex from another GT simplex, then we get a locked set. So here in the denominator we get a 2L, which is the line segment, and on the numerator we are getting another line segment, but that is the output line segment for a locked set, not for the output line segment of the GT simplex. So when seeing this kind of expression, we will instantly understand all these things together. And similarly, for the right hand side also, one locked set is divided by one line segment, and locked set is also the output of the line segment of the locked set is taken, and this forms a triangle. And L cos square theta by L is also a triangle, because these two triangles are similar, and equality of this kind of equality are treated as the similarity of the two different triangles. In the left hand side of the next expression, like sine cube theta is equal to 3 into sine theta minus sine 3 theta by 4. Here also you can see that one theta is involved and one 3 theta is involved. That means there are two kinds of similar triangles are interacting in this expression. One right angle triangle has a theta 90 minus theta and 90, and another triangle has the 3 theta 90 minus 3 theta and 90. These two kind of triangles are interacting here, and on the left hand side we are getting 3 triangles glued together, and so we are getting one output line segment, and that output line segment is divided by L, and so it is forming a triangle where L is the input line segment, and L into sine theta into sine theta into sine theta is generating a output line segment, and these output line segments are glued at a point and forming a triangle. And I have explained in detail in previous videos where how this division creates a triangle, and all the other line segments attached to the GT simplexes are also carried together, and those are also interacting with each other in the different theorems, but those are not directly interacting. Only output line segments are interacting here. On the right hand side of this expression, we can see 3 into sin theta minus sin into 3 theta, which means the L into 3 into sin theta, where if the initial line segment is multiplied 3 times, then it is taken as the hypotenuse, and then perpendicular is taken, and in this way the output line segments forms in the numerator for this expression as a output line segment for a lot set. Because here minus is there, so it is, the whole expression is not a GT simplex. The 3 sin theta is a GT simplex, sin 3 theta is another GT simplex. Obviously these two things are triangles, and triangle is a part of GT simplex, and that is a GT simplex also, the simplest form of GT simplex. And on the denominator there is a 4L, which is a 4 times line segment, and we can treat it as a triangle also. The output of the denominator is the input of the whole set, and output of this locked set is the numerator of this whole set, and these two line segments making a triangle, and the locked sets, the remaining line segments are also present there. We have different kind of theorems coming out for those kind of additional line segments here. Now for every kind of such expressions, here we can see on this third expression has the sin to the power 4 theta is equal to 3 minus 4 cos 2 theta plus cos 4 theta by 8. Here also a numerator has a locked set and denominator has 8 times of L, and on the left hand side we can see 4 triangles, 4 similar triangles are glued, because 4 to the power 4 is there, sin theta into sin theta into sin theta into sin theta. That means the 4 different triangles are glued, where the seed angles of each of these triangles are theta. So 4 similar triangles are glued. One perpendicular is becoming hypotenuse of the first. The second triangle has the hypotenuse which is aligned and scaled to fit for the first, and now the third triangle has the hypotenuse which is aligned and scaled to fit the second perpendicular. In this way the 4 triangles are formed, and as per axiom of geometrifying trigonometry, we have already seen that every multiplication has the 4 symmetries. So when the power is 4, when 4 sin theta are multiplied, so 4 to the power 4, 4 to the power 4, 4 4s are 16, 16 4s are 64, 64 4s are 256. So for sin to the power 4 we can find 256 different output line segments, and all are valid. And in the right hand side also we will get several kind of locked sets with the several different reposition conditions of the output line segments, and 8L is also 4 types. Ultimately we can get multiple number of lines triangles, and out of this there are several natural summability conditions, and for that reason we will get different kind of triangles. Now in this video we will try to examine that how many triangles are glued and how many different behaviors of these kind of locked sets can have, and in our next videos we will examine these numerators also with the different kind of pictures, with different kind of re-examination of the orientation of line segments. Here in one expression we can see that sin to the power 5 theta into cos to the power 5 theta, which means we will have 10 number of triangles, similar triangles are glued in multiple ways. And how many type of ways we can get this gluing? We will get 4 to the power 10, that is 4 to the power 5 ways of gluing in the sin theta, and 4 to the power 5 ways of gluing of cos theta, and all of these things are not commutative. So sin to the power 5 theta into cos to the power 5 theta is not same as the cos to the power 5 theta into sin to the power 5 theta, and these are not at all same as the sin theta into sin theta into sin theta into sin cos theta into cos theta into sin theta into sin theta into cos theta into cos theta. In that way also we can write, and in that case we have the 5 sin theta multiplied and 5 cos theta multiplied, and we can juxtapose all these things in factorial 10 ways, and so we can get factorial 10 ways of arrangement. And for every multiplication we have 4 times symmetry. So factorial 10 into 4 to the power 10. This number of pictures are possible for the left hand side. So geometrifying trigonometry is a huge subject where every simple trigonometry expression can have large number of line segments, and the large number of possible line segments will be there, and all of these line segments will not always become naturally summable. Now in the case of natural summability conditions, we are trying to explain here the THEP arrangements also. The THEP arrangement has the additional 43, minimum 43 different kind of line segments, and all these line segments are attached to every such generated line segments, and we can get 43 times more number of possible line segments. With that we can do data mining so that we can generate large number of identities also. With that we can examine the large number of topological data mining on the data sets. Ultimately, when we have crossed the 2022 AD, and now we have powerful computers, now we have several large number of data structures with the data mining facilities, now we have the machine learning facilities and neural network facilities. So why not we will enlarge the number of data coming from every single trigonometry expression, and we can do deep learning on that to generate deep level of theorems which have the geometric intricate understanding, so that we can get very deep kind of insights from the arrangements of these line segments, which we can get from every trigonometry expression. Up to 1600 or up to 1700 we were trying to reduce problems such that we could handle things easily. So Ptolemy made the trigonometry charts, and then slowly and algebraic systems came up, and we tried to solve things easily, and we tried to convert everything into numbers so that we can at least get some value. We were trying to get some numerical value to get some decisions. But the story changed after supercomputers came in, when computers become cheaper and when data mining became easier. Now we can think reverse also. Now our motive is not to reduce the problems to single simple numbers. Now our problem is to get more and more number of data from simple things, such that we can get better, deeper insights. We are now in the motive to get more geometric insights from the trigonometry expressions which we already have. Now we are trying to get some deeper homology properties, we are trying to get some homothety properties, we are trying to get some deeper cohomology properties from trigonometry expressions. This kind of motive was not there before 1998, or this kind of motive was not there before 2013, because large powerful computers were not available, and so we could not dream about getting deeper insights about the topological data mining on simple things. Now the things are cheaper, and now databases are cheaper, now querying mechanisms are cheaper, and machine learning systems is doing fantastic. And at this situation we are not bothering too much to reduce down the problems to single number. Now our motive is changed. Again we are now moving towards expanding our data set and getting deeper insights from those data set. So geometrifying trigonometry has the motive to expand the data set from given trigonometry expression, and we can get large number of interlinked entangled line segments, and from that we want to get deeper insights of trigonometric properties inside topology, or topological properties inside trigonometry. We are trying to get the Euclidean properties with the Eulerian characteristics. Now we have the dream to get the Betti numbers, or we are trying to get the number of n-dimensional volumetric properties from the two-dimensional trigonometry expressions. Now our dreams are changed, now our motives are changed, because data mining facilities are with us, now machine learning facilities are with us, now neural network facilities are with us, and large databases are available with us. We can do large language modeling, and we can train TensorFlow or PyTorch systems with the line segment data. Now we are not bothered too much with these point clouds, because several kind of point clouds data mining systems are also available with us. Now we are not in the fear that we have to reduce the number of data to handle things. Now we can handle much bigger number of data. So we are now trying to go into deep detail of topological properties which are hidden inside trigonometry expressions. So Sanjoy's geometrifying trigonometry has the target to identify the nature of alignments of line segments for different kind of orders of writing of trigonometry expressions. Now we are trying to explain the things in order of writings, and before going deep into the THEP arrangement, suppose we are doing the simplest line segment construction from the trigonometry expression. Suppose there is a right angle triangle like this, where pivot point is there, stretch point is there, and nodal point is there. We have already discussed in our previous video that in geometrifying trigonometry we explain trigonometry not only with the right angle triangles, we can deal it with any kind of triangles, but for the simplicity now in this video we are taking a right angle triangle here, which is a right angle triangle, and where at the stretch point we have a right angle present there. Now in our school days we used to write 1 plus cos theta plus sin theta. Sometimes we used to write it 1 plus sin theta plus cos theta. Sometimes we used to write it as cos theta plus sin theta plus 1. Sometimes we used to write it as cos theta plus 1 plus sin theta. All these things are different meaning in geometrifying trigonometry. All these things were having the same value in normal traditional trigonometry, but in geometrifying trigonometry the order of writing has an entirely different meaning. The semantics is geometric. So how to interpret this kind of orders of expressing things are very important to know and understand. Suppose we have a right angle triangle which has a hypotenuse, which has a base, and which has a perpendicular. Now we have two hands. With one hand we can catch a line segment. Suppose we are holding the line segment tightly at its own position, and now we can take a scissors and cut any node. If we cut the node at the stretch point, then we can see that we have already hold it here in the hypotenuse, and now when we cut the point at stretch point, the perpendicular behaves like a spring and it straightens and gets aligned with the hypotenuse. In the same way, the base, which is also attached with the perpendicular at the stretch point, which is also behaving like a spring, and it springs out and gets aligned with the line segment as if it was a rubber pipe, as if they were tied here at the stretch point and they are getting straightened. And now when these are getting straightened, then we will get three line segments at the naturally collinear in this way. And since we have holded the hypotenuse, so both are stopped here to make it collinear with the hypotenuse. In this way we are getting the order written as the base was the, and when we are holding the hypotenuse we are considering it as a 1 or L, and now the base is L cos theta and perpendicular is L sin theta. So the expression is becoming, the order of writing is L cos theta plus L sin theta in this way. And when we are writing it as a L plus L cos theta plus L sin theta, in that case we will consider that the writing L plus L cos theta plus L sin theta means our perpendicular is also attached with the cos theta plus sin theta is there, so we have to cut it at the nodal point. So when this base will spring away from the point, then the sin theta will get constructed here like this, and L plus cos theta plus L sin theta will work here like this, and this length is same as this length is collinear with that hypotenuse because we have folded it here, and then these two lengths are same and it will spring up in this direction. In the same way, if we think of the cutting at, if we cut the point at uh, pivot point, then the whole thing will spring up like this, because the sin theta will unfold in this way, the perpendicular will unfold in this way, and the base will go at this point because we have cut it there. In that case, we will understand that hypotenuse plus perpendicular plus base. So we have to think that where we are holding the line segments and how we are cutting the points. In that way, the line segments are forming. When hypotenuse is given and we have to find base, then we use cos theta. And when hypotenuse is given and we want to find perpendicular, we then multiply the hypotenuse with sin theta. Geometrifying trigonometry interprets it as the line segment given, the denominator is the in given line segment, that is the input line segment, and output line segment is the what is constructed. When cos theta is constructed, when the base is constructed, then it is b by h. That means hypotenuse is given and we have to construct base. In that way, when we are doing the sum together as h plus b plus p, then we have to understand where we have hold h and then we have cut the points at nodal. So b plus p are in attached way, and that is attached with the hypotenuse. So where to take one, in several pictures in Wikipedia or in several books, you will see that in the GT simplexes or in the log set, some line segment is taken as the 1. That means that initial line segment L is tightly held on the 2D plane and that is not moving. That is kept fixed, and all other line segments are generated due to the trigonometry expressions are charged on that, and in that way several line segments are formed, and some of these line segments are forming a square, some of the line segments are forming a trapezium, some of the line segments are looking like concentric circles are forming due to the different points are forming there, and this kind of geometric properties or topological properties are coming out from the given line segment and trigonometry expression. Our target is to examine the order of line segments written in such a way, and we have in this diagram we have seen that in this way we have made the enforced collinearization due to the unfolding of the line segments, due to cutting of the points. If we cut at the nodal point and hold the base, then we will get this kind of straightening, because this will spread out here like this, the perpendicular will spread out like this, and this hypotenuse will spread out like this, and they will straighten to a single aligned naturally summable condition. In the same way, for every kind of collinearization, we will see that there is a unfolded nature. The base is unfolded and straightened as the perpendicular, the hypotenuse is unfolded and straightened along the perpendicular. That means the perpendicular was held and we have cut at the pivot point, which means these two lines are spread away. So writing style of the trigonometry expressions tell the story of where which line segment is hold tightly and where the point is cut with the scissors such that the straightening happened. This whole story is hidden inside the order of writing the line segments in any log set. Suppose we can write it as L plus L cos theta plus L sin theta. We can write it as L sin theta plus L cos theta plus L. We can write it as L cos theta plus L sin theta plus L. In that way, we can write the L plus L tan theta plus L sec theta, or we can write L sec theta plus L cot theta, L sec theta plus L tan theta plus L, or we can write it as L cot theta plus L sec theta. From these kind of expressions, we can understand which line segment was held and which point was cut. So holding and cutting is also a axiomatic instruction in geometrifying trigonometry, because that is also a very important axiom in geometrifying trigonometry, that the order of writing these summations tell a different story. In our traditional trigonometry, this kind of in-depth understanding of topological behaviors of cutting and straightening was not discussed. But in geometrifying trigonometry, we are having more power to generate more number of line segments and to generate more number of data, so that we can do examination on these large number of data sets, so that we can generate more theorems, we can generate more identities, and even we can ask more deeper questions on trigonometry expressions. Suppose we were never asking up to the time before Sanjana's geometrifying trigonometry, we were not never asking that how many similar triangles are glued in these kind of expressions, because these kind of questions were never asked in school days, because this kind of subject was not available. There was no such subject which could automatically generate pictures from trigonometry expressions, and there was no such subject before geometrifying trigonometry which were generating large number of pictures out of trigonometry expressions with all symmetries taken care. And so it was never expected that someday we can inquire these kind of geometric queries from the trigonometry expressions, and it was never thought that we can do topological data mining on the trigonometry expressions. Some very simple trigonometric expression can have large number of geometric inquiries possible, large number of topological data mining possible, and several large number of topological theorems can also come out from simple trigonometry expressions. And these kind of insights were not there before geometrifying trigonometry, so we could not expect that this kind of inquiries were possible. Now we are trying to give a simple brief about a THEP arrangement systems, and THEP, the Thales, Hipparchus, Euclid, Pythagoras before Ptolemy. And these are special kind of line segments, special kind of locked set you can think, where some arbitrary lines are taken which are important for some geometric or topological analysis, because these kind of line segments are sometimes giving deeper theorems, and several such line segments we can make, and then we can consider that any of the line segment is a L for that given THEP arrangement. We can think that it is a L for given THEP arrangement, and we can get several benefits out of that. Suppose any line segment of this THEP arrangement is taken as the initial line segment, and now we are aligning and scale to fit this line segment with all the line segments generated due to the trigonometry expression. Suppose there are 6,000 number of line segments are formed in a trigonometry expression after all symmetries are taken, and we can attach this special THEP arrangement where at least 43 line segments are there. We will talk about all the detail of these line segments or the THEP arrangements, which is a special kind of locked set. And suppose we are taking that as a block, as an AutoCAD block, and we are doing align and scale to fit of the initial line segment of that THEP arrangement, say the L of the THEP arrangement. For that L for THEP special locked set, that is a special locked set, and that is glued and aligned and scaled to fit with all the generated line segments for any given trigonometry expression. So suppose there are 6,000 line segments, and all with that we suppose here are the n number of line segments we have taken in a THEP arrangement, and that is aligned and scaled to fit to all of these. Then 6,000 into 4n number of line segments are formed, and that is another huge big database. And from that we already know when we are generating the THEP arrangements for a special purpose analysis, then we have already planned for the kind of analysis we want to do. And these line segments are sometimes one is the root 2 times these, that means the diagonal of a square made with this line segment, or cube root of these root 3 of these means 2 triangles are glued and 3 triangles are glued in that way, the 30 degree, and these kind of things are already made with there. And then we are gluing the whole sets with all the output line segments there. And since in geometrifying trigonometry every line segment has a unique nomenclature, so ultimately after generating these things in the row of the data set which is formed for the machine learning database, we can have every row have a unique line segment information. And normally for the data set, every triangle is represented in a single row. And when the machine learning system runs those things, then we can have a large number of data sets with the THP arrangements attached with every output line segments at every stages of output line segments generated in the process. In that way, we can have a large number of data set of the line segments present there, and from that we can do the inquiries like how many similar triangles are forming in this case, what is the perimeter forming in this whole log set, what are the isoperimetric quadrilaterals forming inside this whole large number of data sets, how many of the collinear and equal sized line segments forming in the process. We can think of, is there any concentric circles forming in this large number of points, endpoints of the line segments. We can inquire that how many of the midpoints of line segments are concentric, are forming concentric circles. Is there any concentric circle which is capturing more number of points in the whole GT simplex point sets? And these kind of questions, these kind of inquiries and topological invariants we can examine from the large number of line segments and large number of blue triangles or large number of log sets forming due to the trigonometry expressions are passed through the mechanisms of geometrifying trigonometry. Geometrifying trigonometry has large number of algorithms inbuilt within that, such that it can parse the trigonometry expressions and can generate data set for data mining. And we can think it as a dynamic programming kind of thing, where it generates data. It generates the data for triangles, it generates data for the line segments, it generates data for different points alignments, and all of these data sets are formed for 0 degree to 30 degree to 360 degree for the whole set of the cases at the 0.01 degree deviations. And we can take looping on all these things for theta is equal to 0 to 360 step 0.001, and in this way can get 360,000 number of log set variants, and everywhere for every of these variants there can have the 6,000 to 8,000 number of line segments. And so large number of line segment data are formed inside the database, and from that we can find the inquiries like that, what are the invariants which are common from theta is equal to 0 to theta is equal to 360. And if that kind of property, suppose 6 particular line segments are forming a hexagon, proper hexagon for theta is equal to 0, and if those 6 line segments are forming hexagon for 0.1, 0.2, 1 degree, 2 degree, 3 degree, for every angle theta, if we are getting the hexagons of different sizes, but those 6 particular line segments are forming the hexagon, then that is an invariant in the topological analysis done on, that is a topological invariant that we can get. And these kind of insights were never examined before Sanjoy's geometrifying trigonometry was there. So we can think that it is going to give us different kind of topological analysis. We can get several homological properties, we can get several deeper invariants in our geometric understanding on trigonometry expressions, and these kind of examinations, these kind of inquiries were never done. And to increase this number of invariance analysis, we are using DHEP systems so that we can get more number of line segments to exhaust our systems with more number of data sets, so that we can examine more insights, and so that we can examine more kind of invariants hidden inside the trigonometry expressions. And these kind of things were never done before, because no one was too much interested to do these things, since computer was not so much powerful to do data mining over these large number of data sets just 15 years back. So we cannot expect that people could become interested to do these kind of things. Now computers are more powerful, the large language models are also there, the data mining facilities are improving, so we can take millions of line segment data or triangle data together to do some data mining on that, and to do some theorem proving, and we can expect that we will get more deeper insights out of the trigonometric insights from the trigonometry expressions, and geometric insights from trigonometry expressions, or topological insights from trigonometry expressions, and where we wish that we will get large number of invariants also, which were never examined before 2018, because these kind of data sets are started preparing from 2017. So Nath is working on this from 2002, but he could get making of these data sets from 2017. So before 2017, this was not expected that these large number of data of line segments and triangles are going to get available to do the analysis, and large number of point sets which is forming a 2D point cloud, a large number of line segments which is making the line segment cloud, and we can think it in that with the meshes of some non-standard grids, or like the Delaunay triangulations, or like Sierpinski triangles, or like any kind of fractals. Big fractals are forming with the line segments due to the trigonometry expressions. And for example, if there is the left hand side and the right hand side with such big number of expressions, and where the factorial of these are the permutations, all the different permutations will get the different kind of geometries, and for every different kind of geometries the position of the output line segments changes. So the insights also changes due to every kind of permutations, and every kind of permutations have different kind of nomenclatures, and from that nomenclature we can pinpoint the geometric construction which is carrying certain kind of invariants. All kind of permutations is not going to carry every kind of invariants. So these are also the insights that we can wish to get from the data mining on the topological data